All right, we're rolling. So we're going to talk about static electricity first, and we're going to discuss the nature of static electricity, discuss lightning protection, and list nuisance and useful charges. Static electric discharge shock. We've all scooted across the floor in a carpeted room, grabbed the doorknob, and gotten shocked. That was a DC shock, direct current shock. And you've slid across the seat maybe and grabbed the door handle. Maybe you've, give me another example. You what? From your hair, you could do that. That's one of the original ways they discovered electricity, remember? We'll get to that in a second. Okay, static charge nuisance or useful. Static charges can be a nuisance or can be beneficial. Electric shocks can be annoying. Electrostatic discharge can ruin sensitive electronic equipment. If you work, the crew that worked on construction at the new expansion of Intel computer chip company, they were required to wear around grounding straps. Even though they were in the same part of the building where they're making the chips, they had to wear grounding straps around their ankles and be grounded at all times so that no static discharge could build up, because that's very sensitive equipment. Old copying machines and other devices rely on the use of static electricity. Current copying machines don't work exactly the same way as the one that the book is talking about. Originally, they rubbed hard rubber against wool or against glass to create remember the guy was talking about this that invented it, and he called them electrics and non-electrics. And so probably he was calling the wool the electric in the case of the hard rubber, or the non-electric in the case of the glass. Okay, some useful uses. Electronic air filters called precipitators use static charges to attract small particles in the air and trap them in the filter. You've seen those on TV, I'm sure. They're still very popular. They're a great way to get all the crud out of the air, because anything that can be charged can be trapped, right? Okay. Electronic charges build up on insulators. Very important fact to diodes, capacitors, transistors, things like that. And a static charge can be positive or negative. Okay, this is kind of a diagram of a precipitator. It's negatively charging the plates, and so anything that's positively charged goes through and sticks to the plates. Very simple stuff. Originally, way back, way back, there was a thing called the electroscope, which is an early device that indicated the polarity of a charge. And these leaves right here that the little red arrows are pointing to would move in or out depending on whether the thing that it was looking at was positive or negative. So here we have a charge pin, and the thing is moving the little leaves, as they're called, out a little bit. Best example of static electricity that you know about is lightning. Very, very forceful, right? Does everybody know how Mike Holt became an expert on grounding and bonding? Because he lives in Florida, where there are 800 times as many lightning strikes as there are here in California. 800 times. So his little office where he produces his code videos has been struck by lightning 7 times and burned to the ground 1 time. So he became an expert on grounding and bonding the hard way. And I want to tell you now, this is like way out of the ballpark, way early, but grounding is protection from lightning and other unusual strikes of electricity that are not expected. Bonding is where you tie the whole system together, and that whole thing about equal potential plane and all that good stuff only happens in bonding. And they're totally separate ideas. They just have to be tied together at one point, the grounding and the bonding point, called the main bonding jumper at any electrical system, and that's the only place it's supposed to be tied together. Okay, but that's a little ahead of things. Lightning rods are used to help protect objects from lightning. Lightning rods provide a safe path to channel the electrical charge. And an arrestor can be used for protection also. What is the difference between a rod and an arrestor? Yes, the difference is that the rod is on the building or structure that you're protecting, just like this little lightning rod is sticking up in the middle of the roof. And Mr. Holt found out that that's not always what you want, because some of the electricity may go onto a wet, dirty roof, because wood is a very good insulator unless it's wet and dirty. Then it becomes somewhat of a conductor. And if you hit it with, let's say, 400 million volts and 400,000 amps, it's going to get very, very hot. What does even damp wood do when you get it, say up to 500 or 600 degrees Fahrenheit? It bursts into flames. That's correct. So even though it's being rained on and everything else, it still will burst into flames because it's so hot instantaneously for a couple of seconds that you just can't deal with it. Okay, so everybody knows about using static electricity to paint. What is this called? Powder coating. Thank you. Powder coating depends on static electricity. And the inside of conduits that are made at Rob Roy are powder coated so that the paint is bonded to the metal so it never comes off. Great stuff. Rob Roy's, just thinking of Rob Roy just the other day, and got a tour of their plant and got certified as part of the corrosion college at Kilmer College, and great stuff. Static means it's not moving. This is a review of what we've talked about, hopefully. Object is positively charged by removing electrons. Object is negatively charged by adding electrons. Now, doesn't that seem counterintuitive, exactly the opposite of what you would think? Does that seem like that would be the opposite of what you would think? Okay, and charges accumulate on insulator materials, very important capacitors and transistors, and lightning is an example of natural static electricity. That is a huge nuisance, right? Okay. Now, I'm going to hit pause for a second while I pull up another little thing. Hit record again. All righty, now we're going to talk about magnetism now. And it's kind of in a bad place. Let's drag this over here. Sorry about that if you're watching again later or something. I'll try and get that out of the way. Discuss properties of permanent magnets. Discuss the difference between the axis poles, and discuss the operation of electromagnets. All right. Oh, I guess we have more. I thought I'd pasted this together. Determine the polarity of an electromagnet. The direction of current is known. There's a rule that's related to this that you're going to remember forever and ever. Discuss different systems. Let's see, define terms. Let's move along. The Earth is a magnet. Okay, that's kind of true. The Greeks knew about magnetic forces 2,500 years ago. The first magnetic stones were found in Magnesia near Asia Minor. That stone was called magnetite. Magnetite was noticed to attract iron. A simple compass was invented using magnetite a long time ago. The compass stones or leading stones became known as lodestones, aligned with the Earth's magnetic poles. Okay. Earth's axis poles and magnetic poles are not aligned. You guys all know that. The angle of declination is the difference between an alignment between the Earth's magnetic pole and the axis pole. In other words, how much off from true magnetic is the center north pole? That's called declination. Earth's magnetic pole is located in the southern hemisphere, not the northern. Okay. Here we have one of the first uses of magnetite or magnet. And if it's a north pole, and it usually is, it's pointing at the south pole of the Earth, right? Okay, the electron theory of magnetism. Permanent magnets do not require any power to maintain their field. Energy is required to create a magnetic field, but no energy is required to maintain a magnetic field. This is one of the basic laws of magnetism. Okay. And man-made permanent magnets are much stronger and last longer than natural magnets. There are only 3 substances that form natural magnets. I want you to remember this, so if you're in your book or in your notes, please write down iron, nickel, and cobalt. Those are the formulas for the original magnets that man created. We've come up with different formulas now for slightly different ones, which we'll talk about in a little while. But the basic formula is what? Iron, nickel, and cobalt. Have I said that 3 times? Okay. Anything I say 3 times, you're probably going to see on a quiz. You know that, right? Everybody knows that? If you don't, you know it now. Electron pairs generally spin in opposite directions. Okay. The spinning action causes each electron to become a tiny magnetic permanent magnet. Electrons tend to form pairs spinning in opposite directions. These pairs negate each other's magnetism, and magnetic materials have some electrons that do not have their magnetic canceled in a pair. These magnetic materials, again, iron, nickel, and cobalt, have regions of magnetic polarity called magnetic domains. Magnetic domains. When the magnetic domains are aligned on an axis, the material is magnetized. When the magnetic domains are in disarray, the material is not magnetized. So material can be magnetized and demagnetized, right? Okay. Now that's what I would call a silly picture. And here we have, for those who don't know, when you go get a, what is this big round thing they slide you into? I've forgotten the name of it.
CAT scan?
It's a magnetic resonance imaging device. And from the name, you can kind of tell what it does, right? You know what it does to your body? It takes all the electrons in your body, every last one of them, and lines them up just like this. They're all lined up the same. And then they release it. And they watch the change. And they can see the change. And that's what makes those colors on the MRI screen, the changing magnetic domains. Isn't that cool? Okay, so yes, you can be completely magnetized. Okay. Now, 3 classes of magnetic materials. There are 3 classes of magnetic materials. They are ferromagnetic, paramagnetic, diamagnetic. Ferromagnetic, paramagnetic, diamagnetic. Ferromagnetic, paramagnetic, diamagnetic. Okay, and once again, we're going to define these. You need to remember these definitions. Ferromagnetic materials are easily magnetized. Easily magnetized. Examples of these are materials like iron, nickel, and cobalt. What a surprise. Paramagnetic materials are not easily magnetized. Examples are platinum, titanium, and chromium. Diamagnetic materials cannot be magnetized. Diamagnetic cannot be magnetized. So easily is ferro, somewhat para, and diamagnetic is not able to be magnetized. You need to know those definitions and those names and be able to match them later on. Okay, diamagnetic materials can be metal or non-metal. Magnetic lines of force tend to go around magnetic materials. Examples of diamagnetic materials are copper, brass, and antimony, whatever that may be. Okay, magnetic lines, you know they're called lines of flux. Flux is represented by the Greek symbol pi. Magnetic flux lines repel each other and never cross. Okay, magnetic flux lines do not flow but have a north and a south direction. Actually, kind of a north and south polarity more than a direction. Okay, magnetic flux lines form north poles and south poles. Okay, just said that. Unlike poles attract and like poles repel. I think have we talked about who discovered that already? We did, last meeting. Yes, we did. You'll see. You'll remember. Suddenly, yeah, I think we have. Okay. Opposite magnetic poles, flux pattern. Okay, that's cute. Like magnetic poles. Opposite poles, magnetic attract, and like poles, repel. Motors are built on that theory. Whenever electric current flows through a conductor, a magnetic field is formed around the conductor. That is always true, whether it's DC, AC, whether the wire is wound or whether the wire is not wound, whether the wire is wound around a piece of steel or not. Doesn't matter, it always creates some electromagnetism, okay? Magnetic fields usually only last as long as the current is flowing. And this is kind of the basis of that guy's theory, Fleming's left-hand rule, okay? The fingers represent the windings. The thumb represents the direction of magnetic polarity, and I don't remember what the finger stands for. Okay, increasing the current flow will increase the magnetic field strength. That's a very important idea to you in motor control. Turns or loops of wire also increase the magnetic field strength. So wrapping a wire around just wrapping them around in a circle creates a stronger magnetic field. And also you can increase the magnetic strength by winding them around a piece of iron. Wind the wire into a coil, increase the current strength. Already said that. Core material is the base that the wires are wound around. Non-metallic core materials are referred to as air cores. In other words, they don't really promote any more magnetism. Cores made from magnetic materials like iron greatly increase the field strength. Most transformer windings are wound around a piece of iron. What most people don't realize, and I'm going to tell you now so you're not confused later, is that when you see a drawing of an input winding and an output winding, they're shown kind of like fist windings, right? And it shows parallel lines in between that represents the iron core, and they're facing each other. Well, that gives you the misimpression that they're wound on different pieces of iron. It's not true. They wind them on one piece of iron. They're wound at the same time. Right? Got it? Okay. So that drawing is just so that you can see there's an incoming winding and outgoing winding. A transformer is electromagnetically coupling current coming in, current going out, without having any mechanical or electrical connection, right? I'm getting ahead of myself, sorry. Okay, permeability is a measure of a material's willingness to become magnetized. This is a definition you need to know, permeability. An air core has a permeability of 1. An iron core provides an easy path for flux lines. Flux lines become concentrated and the field strength increases. Permeability, the ability to be magnetized. Reluctance is the resistance to magnetism. Now, saturation occurs when all the molecules of magnetic material are lined up. So when they send you through an MRI device, it is magnetically saturating your body. Is that correct? Yes. And then they release that magnetic force and watch what happens after that. Residual magnetism remains after the magnetizing forces stop. This is a very important idea. Let's say we have a motor winding. We have two motor windings that react with each other. If we have a very small winding that turns around inside a very large winding, if we magnetize the little winding, it's not going to have much residual magnetism, right? But if we magnetize the big winding, we're going to have a lot of residual magnetism. And what if we want to reverse the polarity of that magnet? What's going to happen? There's going to be some residual magnetism that's going to be fighting changing the polarity. And in the motor, we'll talk about that, in about 6 months. Okay, air core increases the number of flux lines per square inch. I mean an iron core. Sorry. There are 3 different measurement systems. The English system, the CGS system, and the MKS system. Knowing those 3 items will not be enough when we do have a quiz on this. That won't be enough. You'll need to know what that means. Okay, a unit magnetic pole produces a force of 1 dyne. In what system is a dyne? You guys have read this. Tell me what system a dyne is in. No, you tell me. You've read the book. The polarity of an electromagnet can be determined using the left-hand rule. Whose left-hand rule? Fleming's left-hand rule. Fleming was a really bright guy. Okay, when the fingers of the left hand are placed around the winding in the direction of current flow, the thumb will point to the direction of the north magnetic pole. Remember I told you that I couldn't remember what the fingers sticking out means? Now you know why. Nobody told me, I guess. Okay, well, this is true, but this finger usually sticks out and indicates something else, but we'll talk about that another day. Demagnetizing an object is accomplished by causing the molecules to become disarrayed. An AC magnetic field can be used to demagnetize an object because AC is going back and forth, right? So it might disarray the electron spin domains. Heating or striking an object will also cause demagnetization. So when you drop your hard drive, you may do damage to it in more than one way. Okay, single-phase AC stator windings, and we're going to take an AC winding. This is a really big winding, a single-phase AC stator winding. It's a gigantic winding, and we can stick anything we stick in there is going to be subjected to a great deal of magnetism, especially if we're running DC, it'd create more magnetism, I believe. Okay, demagnetized by striking, got that. Okay. Many types of magnetic devices. Speakers, an example of useful magnetism we put to work. Okay. Everybody knows how speakers are made. Does anybody know about electrostatic speakers? Magnaplaners? They're great speakers. I've got a buddy that's got a pair of what are called magnaplaners. They're electrostatic speakers in them. They look like Japanese dressing screens. And they create a gigantic magnetic field and move huge amounts of air. They're wonderful speakers. Okay, early naturals magnets were known as lodestones. Okay, this is just a review of everything we know. Mag poles, axial poles, like poles attract, all that good stuff. Some materials have the ability to become better magnets than the others. Ferromagnetic, paramagnetic, diamagnetic are in the review thing, so that means you need to know those definitions. When current flows through a wire, we get magnetism around the outside of the wire, even if it's not wound around an iron. And 3 different systems are used. You should be able to identify which one is by the unit. If I tell you a unit, you should be able to tell me whether it's English, CGS, or MKS. Really. Okay, we're going to stop for a second while I pull up my next PowerPoint slide. So just hang on 1 second. Okay, a few notes I want to interject about magnetism that we may have not touched on thoroughly enough, and that's rare earth magnets. Let me get this thing out of this corner up here. I don't think we're going to be using that corner. Okay. are strong permanent magnets, much stronger than the magnets we've discussed so far. Developed in the 70s and 80s, and different ones were developed in the 90s. Earth magnets are the strongest type of permanent magnets made. Because of this, the whole world as we know it is changing. Anybody have little speakers you put in your ears? The only reason those things work is because the magnets in them are very, very small and very, very strong. Okay, that's the only reason they work. Magnets made from alloys of rare earth elements, developed in the 70s, 80s, and 90s. Producing significant, stronger magnet fields in other types such as ferrite and alnico magnets. The magnetic field typically produced by rare earth magnets can be in excess of 1.4 Teslas, whereas ferrite or ceramic magnets typically are 1/2 to 1 Tesla. A Tesla is the amount of force generated by that magnetic device. Okay, there are two types, neodymium magnets and samarium cobalt magnets. The ones in your little headphones, those are neodymium magnets. And rare earth magnets are extremely brittle and also vulnerable to corrosion. So they're usually coated to protect them and from breaking and chipping. The term rare earth can be misleading as these materials really are not rare. Development of rare earth magnets began around 1966 when K.J. Stronach and G. Hoffer of the U.S. Air Force Materials Lab discovered that an alloy of one thing and another had by far the largest magnetic force of anything they'd come across so far. Okay, the rare earth lanthanide elements are metals that are ferromagnetic, extremely ferromagnetic, meaning that like iron, they can be magnetized, but their Curie temperatures are below room temperatures. So in pure form, their magnetism only appears at low temperatures. However, they form compounds with the transitional metals such as iron, nickel, and cobalt are standard magnet materials, and some of these have Curie temperatures well above room temperature. So, the advantage of the rare earth compounds over the other magnets is that their crystalline structures have very high magnetic anisotropy. This means that a crystal of the material is easy to magnetize in one particular direction, but resists being magnetized in any other direction. Now that's the odd part about them. They only magnetize one way. Okay. Atoms of rare earth elements can retain high magnetic moments in the solid state. Consequently, incomplete filling of the F shell, which can be contain up to 7 unpaired electrons with aligned spins. Electrons in such orbitals are strongly localized and therefore easily retain their magnetic moment and function as paramagnetic elements. Okay. Let's see. High magnetic moments at the atomic level in combination with a stable alignment results in high strength. There are two types of rare earth magnets. You very seldom will hear of the samarium cobalt type, but they have a niche purpose in the world. The first family of rare earth magnets really discovered are used less than neodymium magnets because of their higher cost and weaker magnetic field strength. However, they have a higher Curie temperature, creating a niche for these magnets in applications where the high field strength is needed at high operating temperatures. They're highly resistant to oxidation, but unlike neodymium, remember, but the sintered samarium cobalt magnets are brittle, extremely brittle, and prone to chipping and cracking and may fracture when subjected to thermal shock. In other words, sudden heating or cooling. Okay, Neodymium magnets invented in the 1980s are strongest and most affordable rare type of rare earth magnet. They're made of an alloy of neodymium, iron, and boron. May I suggest you write down neodymium, iron, and boron makes up neodymium magnets. They have the highest magnetic field strength and have a higher coercivity, which makes them magnetically stable, but have lower Curie temperatures and are more vulnerable to oxidation. Now, there's a problem with really, really, really strong magnets. You'll be able to see this later.
Oh, okay.
Remember.
Just trying to remember iron and boron.
Should have written it down. That's okay. You can see it again. Okay. Due to the high cost of these magnets, neodymium, I should say, limited their use applications requiring compactness together with high field strength. They've come down in price a lot, so they're used a lot more. Many of the devices you know and love have been miniaturized because of neodymium magnets. Computer hard drives. You've seen now that there's a computer hard drive that is like 2 inches by 2 inches, and it holds a terabyte of information. If it were not for neodymium magnets, that would not be possible. Okay? More efficient generators and wind generators. The wind generators are the first ones to start using permanent magnets and neodymium permanent magnets so that they can make a lot more energy. And as they start changing out generators, my guess is they'll start changing them out to that kind of a generator. Audio speakers fit in your ear, only possible because of neodymium. Permanent magnet motors and cordless tools. I want to stop right here. Permanent magnet motors. I was in a room with, thanks to a friend of mine by the name of Mike Winters, who is was a brilliant high school teacher, and he had a room full of really brilliant people at his school discussing future things that were going to come up. And between the 7 people in the room, they each held on average between 25 and 125 patents to their name, each one of them, all 7 of them. And one of them had invented a new motor, permanent magnet motor, based on neodymium permanent magnets, and it was the most efficient motor ever built. The only problem was, so far they've only made one that creates 10 horsepower, but it was the size of an alternator in your car. Really, for 10 horsepower, that's tiny. That is amazing. And that's the kind of thing that's coming. You've seen the auto show things where they show one of these days we're going to have cars with an electric motor on each wheel, and there won't be any engine. There'll just be this electric stuff. They're talking about, well, that's what they're talking about. They're talking about when they can upsize those neodymium motors up to 50 horses apiece, and they can get them down around this size and put them on each shaft. You could have 200 horsepower, and it would be a third of the weight of your standard cast iron internal combustion engine. Think about that. That's when people are going to like electric motors, when they're fast and really efficient. That's when people really like electric motors. Okay, back to our permanent magnet motors and cordless tools. You've seen the new kind of batteries and the new kind of tools that keeps getting smaller and smaller. It's because of the new magnets, partly. Part of it's because of new batteries. Traction motors and integrated starter generators in hybrid and electric vehicles, self-powered flashlights. Has anybody seen those flashlights that you shake it and it creates its own power? The only reason that works is because that's a neodymium magnet in the middle, creating a great deal of electromagnetic force as you shake it back and forth. What's the drawback of that thing? If you dropped it too hard, you might break it. And if it breaks, well, we won't get into that. Self-powered flashlights employing rare earth magnets for generating electricity. I've got one, and it's just too much trouble at the moment. They'll get better yet. Okay, greater force exerted by rare earth magnets creates hazards that are not seen with other kinds of magnets. So, what kind of hazards? If you got caught in between two neodymium magnets the size of a quarter and a quarter-inch thick, it might break your arm if you get your arm caught in between those two magnets. That's how much force they generate. A lot of force. I think I plugged a picture in here, I hope. And another thing, keep neodymium magnets out of the reach of children. They're coming out with toys, by the way, that are little neodymium magnets, and you can stack them up in a little square shape. They're really cute. Don't let kids get anywhere near those things. There have been cases where young children, let me get this out of the way for a second, who have swallowed several magnets, have had folds of their digestive tract pinched between the magnets, causing injury, and in one case, intestinal perforations, the other the hole, and death. So how do we find out the bad side of things? We do it the hard way. We find out the hard way on everything. Okay, it didn't have any of my pictures in there that I put in it earlier today, or I thought I put in it, but I guess that's okay. I'll be darned. No pictures in here at all, huh? Okay, well, I plugged a bunch of pictures in here, but I guess they're not here. There, I have a picture in there with a neodymium magnet about the size of a pea, a green pea, holding up a 9-pound hammer. Okay? That's how strong they are. They're really, really, really strong. Okay, and that's my presentation on magnets. And we're way ahead of schedule. That's good. So let's take a break. And let me stop this.